Let us see the last part of this partition, final partition of unity. Because this result play a very important role in distribution theory and in Sobolev spaces. So I take let K be a compact subset of Rn and let OI I equal 1 to n open subset of Rn such that K is in this union I equal 1 to n of OI. So we have K is in a finite union of open set. Partition of unity say there exists phi I belong to D of OI for I equal 1 to n. For each I there exists a function phi I, C infinity function, this compact support in OI. Phi I is between 0 and 1, and the sum for I equal 1 to n of phi I of x is equal to 1 on K. This is the partition of unity. It means, look at, remark, if you have a function phi such that the support of phi is inside K. If you take down any function phi such that the support is inside this K, by using the partition of unity, so we can write this function phi of x to be sum for I equal 1 to n of phi I of x. So it means that we can write our function phi to be sum for I equal 1 to n of phi for I. We get a decomposition of phi. If phi is a function this support in K. Because if you look at, if you are in K, if you are in K, so you have phi of x outside, and this sum of phi I is 1. If now you are outside K, so this is equal to 0 and this also is equal to 0. So this equality is 2. And so by using partition of unity, we can write phi has a sum of function like this. But here you will see that for each function here, the support of each phi I is in OI, because the support of the product is inside the intersection of the support. So the support of this function is inside the support of phi intersects the support of phi I. And we know that the support of phi I is in O. So we can write phi has a sum of function and each function has its support in OI. And we will use this decomposition a lot to prove some result. Okay? So this is a partition of unity. Proof of this. I start with this. K is a compact set in a finite union of open set. So I take let x in K. We know that if x is in K, then x is in some OI. So OI is the neighborhood of x. And I use the fact that in Rn, any point has a local, how to say, has a local neighborhood of compact set. Means we use the fact that any point in Rn and any neighborhood of x has a neighborhood also which is compact and which stay in in the first neighborhood. So it means that if I take x in K, there exists Vx, open neighborhood of x, such that Vx bar is compact, such that Vx bar is compact, is a compact subset of OJ. This x is in OJ. It means if I take x in K, I know that there exists some j such that x is in OJ. For this OJ, there exists an open neighborhood such that this neighborhood, the closure of this neighborhood is compact and the closure stays inside OJ. It looks like if x is in OJ, so there exists an open ball, and you take this open ball, you can take the radius small such that the closure also stays in OJ. So for any point in OJ, we can find a neighborhood like this such that the closure is compact and the closure also stays inside OJ. This we can do for any point x in K. We are working in Rn because R is this is the property, the topological property is R is locally compact or R is not locally compact. Locally compact means any point has a compact neighborhood. This is better than locally compact because this is any point. Any neighborhood of that point contains a compact neighborhood. This property is true for Rn. So since I can do this, yes, since I can do this for any x in K, so we have K is in this union for x in K of such Vx. Because for each x in K, I have Vx. So if I take the union of all Vx, this union contains K. And I use the fact that K is compact. Since K is compact, then there exists x1 to xm such that K is in this union for I equal 1 to m of Vxi. This is an open cover, so I get a finite open subcover. Okay? Now I define let for each j between 1 and n, let kj, I define this new set kj to be the union of those Vxi such that the union of those, because here for each I have a family of Vxi, I define kj to be the union of those Vxi such that Vxi is in OJ. Because if you see, when I get this Vxi, I know that by construction Vxi is a subset of OJ. And from here I get an open cover of K. And for this open cover I get a finite open subcover. So for each j I take, I may find some Vxi which are in OJ if j is fixed. So the union of all this is my kj. It means what? For example, if I have Vx2 and Vx3 is a subset of O1, for example, because this V may be Vx1 and Vx3 are subset of O1, so it means that if I define K1, K1 will be only Vx2 bar union Vx3 bar. If, for example, for O1, if there is no Vxi in O1, so it means that K1 is equal to empty set. So I define Kj to be the union of those Vxi bar such that this inclusion is true. This inclusion, such that this inclusion is true. Now here we have each Kj is compact because I have a finite union of compact set, and we have Kj also is a subset of Oj because I collect only the Vxi bar such that Vxi bar is a subset of Oj. If I take the union of all this set, I get a subset of Oj. And we have also K is in the union for j equal 1 to n of Kj, which is also in the union for j equal 1 to n of Oj. I have this. Okay? So,
excuse me.
yes?
I'm not quite convinced because so did you take care of it when for each j for the kj containing the union of those? Did you take care of the fact that k was going to come along those because it's contained in the bigger union of them and then this other finite union? But then I'm not so. Could you explain why that is true?
K is here. Yes, look at what is Kj?
Kj is a union of the vi.
Kj is the union of Vxi. If you take now the union of all Kj, that you get is bigger than this set. Because all Kj comes from element from here. If I take the union of all that I get contains this set. Because each Vxi you take here is in some Oj. Is in some Oj. So this K is in this union. And each Kj is in Oj, so I have this inclusion. Okay? So now if you look, we have Kj is in Oj. And this is open set, and this is a compact set. So I can use Urison lemma. So by Urison lemma, there exists a function beside j in D of Oj such that 0 is less than beside j less than 1 and beside j is equal to 1 where? Is equal to 1 on Kj. For each j, I have such beside j. Now let us define phi j. So we take let phi 1 to be beside 1. And I take phi 2 to be 1 minus beside 1 beside 2. And so on, we define beside how many we have? Beside n. So we define beside n to be 1 minus beside 1, 1 minus beside 2, and so on, 1 minus beside n minus 1, and at the end we take beside n. Now, if you see, phi j belong to D of Oj. Why? Because the support of each phi j is a C-infinity function, and the support of phi j is included in the support of psi j. For example, the support of psi 1 is exactly the support of this one. The support of phi 2 is inside the support of psi 2, and we know that the support of psi 2 is in O2. If you take the support of psi 3, of phi 3, it is included in the support of psi 3, which is a subset of O3, and so on. So each element here is an element in G of OJ. This is 1. 2, we have 0 is less than psi j, and this is less than 1. Because I have product of element between 0 and 1. Because each element here is an element between 0 and 1. So each product here is an element also between 0 and 1. And we have the summation for j equal 1 to n of this phi j of x is equal to 1 for all x in j. Why? Because look at, if you take x in k, arbitrary x in k, we know that if x is in k, if x is a point in k, then x is in k1 or x is in the union for j equal to n of k j. If x is in k1, it means that all these functions are 0 because in each psi 1 is equal to 1 and we have psi 1 in each term. So all this term is equal to 0. So the summation is just psi 1 of x. But since x is in k1, we know that psi 1 is equal to 1 on k. So we get 1. If x now is in this union, it means what? It means x is where? Is in some kj for j bigger than 2. So what we will have is from 3. All this term is 0 because if x, yes, bigger than equal to is for some kj for x bigger or equal to 2. No, we cannot get like this, huh? Because if you see, if x is in k2, for example, if x is in k2, so this term is equal to what? This term is equal to, if x is in k2, after k2 all terms are equal to 0. And it remains only these two terms. But this is 1. And we have psi 1 plus 1 minus psi 1 and we get 1. If x is in k3, which one we will have? If x is in k3, after k4, so we have psi j of x is equal to 0 for j bigger than if x is in k3 bigger than 4. And so we have the first one, this is, we have psi 1 plus 1 minus psi 1 psi 2, and we have plus 1 minus psi 1 minus psi 2, and we have psi 3. But since x is in k3, so this term is equal to 1. This term is equal to 1. This term is equal to 1, and what we will get? Okay, let us write like this summation. We can write this summation. The summation of psi I for I equal 1 to n, this is what? This is psi 1 plus 1 minus psi 1 psi 2 and so on, plus 1 minus psi 1 1 minus psi 2 and 1 minus psi n minus 1, and we have psi n.
You want phi. The first one, summation.
Yes, this is the summation of phi I. Huh?
Yes.
Yes, this is the summation of phi I. And how to write this simply this term? If you see, this is psi 1 for the first term, plus the second term is 1 minus psi 1, factor out. We will have what? Psi 2 plus 1 minus 1 minus so we have 1 minus psi 2 psi 3, okay, plus and so on, and here we have 1 minus psi 2, the last is 1 minus psi n minus 1 psi n. This is what we have. And after this one, what we can do?
The same thing in bracket. In the bracket.
In the bracket we have what?
Psi 2 plus 1 minus.
So we have this is psi 1 plus 1 minus psi 1. If I factor out by 1 minus psi 2, so here I have now 1 minus,
Psi 2 plus.
okay, we have psi 2 plus, and we have 1 minus psi 2. Factor out. We will have what? Psi 3 plus, we have 1 minus, the next will be 1 minus psi 3, psi 4, and so on. And the last will be 1 minus psi 3 up to 1 minus psi n minus 1 psi n. This is what we have. And how to get the formula for this?
Write it as the sum of the product. Because this one is going back to the first one.
Which one?
If you open the bracket now, you return to number 1.
If I open this bracket,
Yes.
yes, so I have,
So just write, let's see, write it as the sum,
this one,
the first one,
this one,
yes, as the summation of the product, followed by product.
yes, product for j.
Yes.
Here I have sum from I to n, sum for j different from I of 1 minus psi I. Is this?
Yes, then
Because in each product, for the first term, what I have?
you have to.
Now we have psi I. Is this? For the first, if I equal 1, if I equal 1,
No, you have to.
No.
You have to take.
This is not equal to.
No, you have to take product up to somewhere. Then you say to k, and then you sum from k to n. It's a double product like that. That's what it has to be. But let's see how. Because the sum I equal to 1. No, you have to.
If I equal 1 here, we will get 1 minus.
No.
Now we start at 2. If I equal 1, we have 1 minus psi 2 times psi 2 plus. No, this
No, you start from.
is not of this.
Just a minute. Yes.
We?
J will stop at I.
This one.
Start from 1. Let's see. And stop at I.
Okay.
And then let's see if it will work. And then I goes from 1. So when I is 1, the product disappears. And then you get there.
And you have 1 minus psi 1 times psi 1.
let's see if the first one will be 1 minus p psi. You want the first one to be 1. So,
Psi I plus
eh?
psi I plus the product.
This one, huh? Is
Yes.
Psi I plus
this
P psi I
plus the product.
here,
Yes.
psi I plus the product. But in the product we take
from 1
for j different from I.
from 1 to
from 1. It has to start from 1.
Yes, from 1 to n.
to I.
Okay. From j from 1 to I of 1 minus psi j. Okay, let us see.
Let's see.
If I is equal to 1, so the first term will be psi 1. And j is equal to
That's
1.
1, yes.
So we have plus 1 minus psi
1.
1. This we don't have it.
This psi.
It's not quite right like this. I don't
Yes,
know.
it's not.
Let me see. No, you don't need plus. I'm sure you don't need plus, but because you have to look at the product is progressive.
So we can just take this one. We can put this one and write this as a product. This we can do it. This one.
Yes, you can do that.
Yes, this is just the first one is psi 1
Correct.
plus. Now this one is the sum.
Correct.
Is the sum.
Of the product.
Is the sum for what? Is the sum. We have psi 1. So we sum for j equal to 2n of product
Yes.
for product for I equal 1. Which term for
To J.
huh?
Try to J. J or J minus 1, but put J first. Let's see.
We have 1 minus for 1 equal 1 to n minus 1, and we have psi I and psi j. I think is yes, I see. For we have for j equal 2, so I is equal to
1 to 2.
no, here it is from 1 to what?
J.
From 1 to
J.
j, yes. This is what we have. Now for j equal 2, so for I equal 1, we have for I equal 1,
1 minus 5
1 minus psi 1,
times psi 2.
psi 2.
Yes. Plus, not times.
We have product.
J minus 1. Maybe you look at n equals 2 because we are taking the first two terms.
Because for j equal 2, we have to take the product, so we have 1 minus psi 1 for I equal 1, 1 minus psi 1 times psi 2.
And then it's
To try to take J minus
J
1.
minus 1.
J minus 1.
Here.
Yes.
Yes.
Here.
Yes, that's what
Now,
it is.
And so for
J is equal to 2.
for j equal 2, you have just I is equal to 1. And we have 1 minus
1 times.
psi 1 times psi 2. For j equal 3.
Yes.
So the first term will be 1 minus psi 1 times
sorry.
no. That's work.
So maybe we can.
For J equals to some 1 to 1, that's fine. Right? Yeah, fine.
Okay, anyway.
We can proceed it proof by checking some example and then check.
So, have homework for one day. Prove that. Prove that this summation of psi I for I equal 1 to n. I think we have a formula. What is that? is I think is 1 minus what?
1 minus psi 1 times.
1 minus psi 1.
No, 1 minus the bracket 1 minus psi 1.
Yes, is 1 minus psi 1 times 1 minus psi 2 up to
1 minus psi n.
psi n. Yes. Prove this formula. This if you get this formula now is finished.
Yes.
Because for any x in k, x is in some ki. And so this term is always equal to 0, and we get exactly 1. So homework, try to do this.
This line does it if you want. It's something to end.
And so we have partition of unity. Anytime we have a compact set in a finite union, we can find this function psi. This function phi I. Each phi I has compact support in OI, and the sum is equal to 1 on K. Even the sum is equal to 1 on some neighborhood of K. A neighborhood of K is an open set containing K. Okay? So, last result, Dubois, Raymond, Lemma. I will not prove you. So, if you have, let f be a L1 log function, means f is integral in is integral in any compact, such that the integral over omega of f times phi dx is equal to 0 for any phi belong to d of omega. Then f is equal to 0 almost everywhere. Then f is equal to 0 almost everywhere. This is the fundamental lemma of calculus of variation. This lemma, if you read a book in calculus of variation, they call fundamental lemma of calculus of variation, because we use this lemma to get Euler-Lagrange equation. So f phi is equal to 0 for any phi in d of omega, then f is equal to 0 almost everywhere. Even you can prove this for any phi in c naught of omega. Here I do in d of omega, but even the same proof allowed to prove that if f phi is equal to 0 for any phi in c naught of omega, then f also is equal to 0. But this one is better than this one, because d of omega is a subset of c naught of omega. So it is better to take this one, because we have only to test in a smaller set. Because if this is true in this smaller set, then it means that this function is equal to 0 almost everywhere. Okay?
I think there's a lot like this in measure theory, right?
Yes.
Riemann-Leibniz measure or something.
But we have only F. Only F.
Okay, I remember. I think I said it from the right.
Yeah, we don't have a second function.
Yes. Yes.
Okay? So let us now start a new chapter, distribution, chapter 2, distribution theory. So we need to make some notation.
Before starting, excuse me, make a comment in this chapter we're going to do, so that when I will read, I know how I can proceed. I know where I'm going.
Here we try to define generalized function. Means, for example, I give you an example. We try to give a justification. For example, if you take this function delta naught,
Correct.
delta naught of x, you say this function is equal to 1 if x is equal to 0, n is equal to 0 otherwise. Okay? This function now, delta naught, is equal to 0 almost everywhere, because this function is equal to 0 except at 0. So this function is equal to 0 almost everywhere. Since this function is equal to 0 almost everywhere, this implies that the integral over R of delta naught of x dx, this is equal to what? Why 1?
0.
Huh? This is 0. If you look at this as a function, if you look at this as a function, so the integral of this function is equal to 0. No, I integrate. Is a real number. Now, I integrate. This is equal to 0. Now, you will see, physicists, for example, they use this integral. And you will see they write that the integral over R of delta naught dx, they write to be 1. Physicists, they use it. They use it and they write this to be 1. And if you look at this as a function now, you are in trouble. Because from measure theory, we know that if f is 0 almost everywhere, the integral of f is equal to 0. But physicists, they use this function and they say the integral is equal to 1 because they don't use the same notion. For physicists, for them, even they consider this as an integral, but it is not an integral. But if you ask to any physicist, they told you the integral of delta naught is 1. But it is not integral, this is just notation. And you will see that this in distribution theory, this is not integral, this is just delta naught has a function, a generalized function applied to the constant function 1. Where delta naught applied to any function phi, by definition will be phi of 0. If you take this definition, delta naught applied to phi is equal to phi of 0. So if you replace phi by 1, so you will have delta naught applied to this function 1 is the constant function applied to 0. And you will get exactly 1. So this is not an integral, but this is just the Dirac distribution applied to the constant function 1. And so, from there, we define more general function. For example, this one is not a function, as you know. This is what we call Dirac distribution. And from there, we try to give a generalization of this kind of function. And you will see, for example, this function, even you want to compute the derivative, you will have problem. Because this function is 1 and 0 otherwise. What is the fraction, the normal derivative you know for this function? You cannot compute because this function is not differentiable in the usual sense. But in distribution theory, we will show that this function is C infinity.
You understand?
Because this is not a normal function as you know. So we try to give a generalization of function. And in the case here, for example, you will see that this function is not differentiable. But in the sense of distribution, this function is C infinity. And so we will try to give a meaning of derivative in the sense of distribution. This one will generalize the notion of derivative you know. Means if you take a function which is differentiable in the classical sense, the same function, you compute the classical derivative and you compute the distribution derivative, they will coincide. We don't change, we just extend. So if a function is fractional differentiable, if you compute the fractional derivative and the distribution derivative, you will get the same thing. You will find some function such that the distribution derivative exists, but the fractional derivative does not exist, like this one. You will see, for example, if you take any function in LP, it is not necessarily fractional differentiable, but you will see that any function in L1 log is the biggest space you can get. any function in L1 log becomes a C infinity function in the sense of distribution. And from there, we can use more general operator and try to solve some partial and pose some partial differential equation. So you will see, if you write a partial differential equation, like for example, Laplacian of u is equal to f. Here, where u is not necessarily, because for this to have a meaning, u must be second 2 times derivative, because the Laplacian you use second derivative. But we try to give a meaning for a function which is not necessarily 2 times differentiable, because we look this equation has an equation in the sense of distribution. So first, when we solve this problem, we find a solution, because we will define what we mean by classical solution and weak solution. Classical solution is a solution such that this function u is 2 times derivative and this equation is satisfied. But it's very difficult to get a classical solution. So we try to look this problem in the sense of distribution. And so we are looking for a distribution u satisfying this equation. If we get this distribution, now we study the regularity of this distribution. And if we put some assumption on f, we can show that the solution in the sense of distribution becomes now a classical solution. So even you are trying to find a classical solution, you cannot go directly. First, you find a weak solution. It is a distribution. And this weak solution, you study his regularity to prove that this weak solution now becomes a classical solution. So we cannot do Sobolev spaces without doing distribution theory, because we will have problem even to define what is Sobolev spaces, because you take subset of LP such that we can compute the derivative. And this becomes a problem, because any function, if you take a function in LP, it is not necessarily true that you can compute the classical derivative. So we try to give a meaning to this kind of derivative, and this is what we call derivative in the sense of distribution. And you will see that any distribution is of class C infinity. Anytime you have a distribution, you can compute the derivative
As you like.
because it is a C infinity function. Okay?
Then let me say one more. What you ask is very, very crucial. Because if you know why you are doing something, like you said, you get motivated. So this is very important, what Sojita has explained. The physicists were right to write this integral as 1. Mathematicians say they are writing nonsense. This is not a function. Our theory says it's 0. But all the things the physicists did were correct. In applications, everything was working very well. And we are saying that they were wrong, so they didn't care until a French mathematician, Laurent Schwartz, decided to find out what was going on. And he discovered that our definition of derivative did not go far enough as limit of f of s minus f of a. It didn't go far enough. So either we define now what we shall mean by differentiation. Not with that ratio any longer. We define it from something else. I don't want to preempt what he would do. With that definition, and then we do this, we come back to realize that the physicists are right. So our notion of functions is limited. So we are going to expand it, like you say, to get what we call generalized functions. That's another name for distributions. So in that sense, what do you mean by convergence? What do you mean by differentiation? What do you mean by integration in that sense? Our function f of x equals absolute value of x. We claim it's not differentiable at 0 because we are narrow-minded. In distribution theory, you differentiate it and you get what you expect. Minus 1, and 0. So the physicists, because of their intuition, they were ahead of mathematicians. So what we are trying to do here is show you, like he said, that our definitions are limited. He would develop new definitions And we studied like baby analysis again. What do you mean by convergence? A sequence here, what does it look like? What do you mean by differentiation? What do you mean by integration? Once we have understood those, we now see that absolute value is differentiable, that this function makes sense. We now have a more general view of differentiation, and that's what we have to work with all through. And when we go to PD, like he explained, you start from that place. You have all the PDs where you will not be what you can differentiate. But we now use this generalized version to get solutions. So it's very, very important. Without this distribution, we cannot go far.
Okay, first let us make some notation. We take, let alpha 1 to alpha n a multi. This is a vector in n over n. Means its alpha I here is an integer. This alpha is a multi and x. And we denote by absolute value of alpha. This is the length of alpha. And the length of alpha is defined to be the sum for I equal 1 to n of alpha I. This is the length. Now, if you take, if f is a function defined from omega to r, we can assume that f is c into d. So we define d alpha of f. This notation, d alpha of f, is just by definition is d alpha, norm of alpha, over, we take dx1 alpha 1, dx2 alpha 2, and so on, dxn alpha n of f. This is the notation of d alpha. Example, if for example we want to compute d square of f x1 dx2, this is just d alpha of f. We are in R2. It's just d alpha of f. Even we are in Rn, even take f to be in Rn to R. This is d alpha of f, where alpha here is equal to what? What is our alpha here? Alpha is 1, 1 and 0 and 0. If now you take alpha, for example, to be 1, 1 and 1 is the last, so this we will get d alpha of f is just what? I compute the length is 3. So this is d over 3 of f over what?
You say the length of 3 with dots in that window?
Yes, I have 0. 0 and the last one I put 1. So the length here